Hi. The last thing I want to talk about before we start building the circuit is the frequency response function of an LTI system. So what happens when I apply an AC sinusoidal voltage to the input of the RC circuit? Now before we do that, let me quick swap my camera out so we can focus on the content. Alright. The frequency response function Hj omega of a circuit is defined to be the output phasor, V out, divided by the input phasor, V in. I'm going to compute this Hj omega for the RC circuit. So step 1 is convert the entire circuit to frequency domain. The frequency domain, or also called phasor domain. We're going to have, here's our input phasor, V in phasor. The resistor stays as is because its admittance is 0. Here's our capacitor, 1 over j omega c. Close the circuit there. And then here's our output, which is V out phasor. That's step 1. Now step 2, apply voltage division. The voltage across the capacitor is V out phasor equals its impedance, 1 over j omega c, over the total impedance, 1 over j omega c plus I, times the input phasor voltage, times V in phasor. So, if I take the ratio of the V out phasor over the V in phasor, I get V out phasor over V in phasor equals Hj omega. This is the definition. Which equals, in this case, 1 over j omega c over 1 over j omega c plus I. So now if I multiply both the numerator and the denominator by j omega c, so times j omega c over j omega c, what I'm left with is 1 over 1 plus j omega IC. This is the frequency response function of the RC circuit. Now before we move on, I'm going to step back for a minute. I want us to think about what's really going on with this frequency response function. If you apply a sinusoidal signal, say cosine of omega t, to the RC circuit, you'll get out magnitude of Hj omega times cosine of omega t plus the phase of Hj omega. Now, this cosine of omega t, through Euler's identity, is the real part of a complex exponential. So that's the real part of e to j omega t. So that goes to the RC circuit, and we get out the real part of magnitude of Hj omega times e to the j omega t plus angle of Hj omega, which I can write this as e to j omega t times e to the angle of Hj omega, and magnitude of Hj omega e to the angle of Hj omega is Hj omega itself. So this equals the real part of Hj omega e to the j omega t. So basically, at the end of the day, what's happening is that I pass in a complex exponential to the RC circuit, pass the complex exponential in, and what do I get at the output? Same thing. The exact same complex exponential at the same frequency, just multiplied by Hj omega. And what I'm going to show you next is that this property right here, where you pass in a complex exponential and you get out that same complex exponential times Hj omega, is not just specific to circuits. That this is a general property of any LTI system. Is general for any LTI system. So let's see how that is. Right now, what you learned is that for any LTI system, the output is related to the input through the convolution integral. So y of t equals the impulse response h of t convolved with x of t, which this equals the integral from minus infinity to infinity of h of tau x of t minus tau d tau. Now, I'm going to pass in a complex exponential, so x of t equals e to j omega t, and I'm going to see what the output y of t is when I pass in the complex exponential. So y of t for the convolution integral is the integral from minus infinity to infinity of h of tau times x of t applied to t minus tau, so e to j omega applied to t minus tau, so e to j omega t minus tau d tau. Now remember, this integral is being performed with respect to tau, not t. So t is a constant with respect to tau, which means we can pull e to j omega t outside of the integral. So this is the integral from minus infinity to infinity of h of tau e to the j omega t times e to the minus j omega tau d tau. And e to j omega t is a constant with respect to tau, so it can go outside. So we have e to j omega t times the integral from minus infinity to infinity of h of tau e to the minus j omega tau d tau. Now notice, complex exponential in, complex exponential out, times the integral from minus infinity to infinity of h of tau e to the minus j omega tau d tau. And it turns out that this is what we define as the frequency response function h j omega. Now let's test it. Let's evaluate this integral for the RC circuit and see if we get the frequency response of the RC circuit. Now, in order to do that, we have to first find the impulse response of the RC circuit. So let's check it. Check result for RC circuit. As you learned in lecture, the impulse response can be computed from the step response by differentiating with respect to time. So this is dy step of t dt, which is d dt of 1 minus e to the minus t over ic, which equals 1 over ic e to the minus t over ic. And now we're going to put this into this integral and see if we get the same h to j omega that we found through phasor analysis. H to j omega, we'll see, equals the integral from minus infinity to infinity. And now something very important here to remember is that this step response, y step of t, was for t is greater than 0. The RC circuit is a causal system, which means that h of t is 0 for all t less than 0. So the impulse response is 1 over ic e to the minus t over ic times u of t. Back to calculating the frequency response function, h of j omega is the integral from minus infinity to infinity of 1 over ic e to the minus tau over ic u of tau times e to the minus j omega tau d tau. Now, since u of tau is 0 for all tau less than 0, this is the same thing as the integral from 0 to infinity, because for tau is less than 0, this product is 0. So this is the integral from 0 to infinity. I can take the constant 1 over ic outside of the integral, since it's just a constant. And we're left with e to the minus tau over ic minus j omega tau d tau. Now I can factor out tau from the numerator. 0 to infinity e to the power minus 1 over ic plus j omega tau d tau. Now this integral evaluates to 1 over ic times e to the minus j omega plus 1 over ic tau over minus j omega plus 1 over ic from 0 to infinity. Now I'm going to expand this exponential. So right now we have 1 over minus ic j omega plus 1 over ic times e to the minus j omega e to the minus j omega tau, e to the minus tau over IC from 0 to infinity. So, at infinity, e to the minus j omega tau has magnitude 1 and an arbitrary phase, we don't know. But e to the minus tau over IC, as t goes to infinity, it goes to 0, because e to the minus infinity is 0. So at infinity, since this one has magnitude 1 arbitrary phase, and then this term goes to 0, this whole product has a magnitude 0. We have 1 over minus IC j omega plus 1 over IC times, at t equals infinity, at tau equals infinity, this term evaluates to 0, minus, at tau equals 0, e to the minus 0 is 1 times e to the minus 0 is 1. So 0 minus 1, which is minus 1, and lo and behold, we're left with 1 over IC times j omega plus 1 over IC. I can multiply this out, so we're left with 1 over 1 plus j omega IC, and this is the exact same frequency response function that we derived through phasor analysis, which you learned in EECS 215. So two important facts that we can get from all of this is that, one, for any LTI system, complex exponential n, I pass an e to j omega t through an LTI system, I get out another complex exponential of that same frequency, but multiplied by the frequency response function h to j omega. And then the second thing is that, if you recall, this integral here, the integral from minus infinity to infinity of h to tau e to the minus j omega tau d tau, turned out to be the frequency response function h to j omega, which tells us that we can compute the frequency response function h to j omega of any LTI system if we're given the impulse response, if we have the impulse response h of t, through the integral h to j omega is defined to be the integral from minus infinity to infinity of h of tau e to the minus j omega tau d tau. So that concludes our introduction for Lab 1, and now we'll move on to Part 2 of the lab, which is building the circuit and taking the appropriate measurements.